All right, welcome back. Welcome back. We're going to talk about today one of the most famous irrational numbers. So famous, in fact, that they gave it a letter as the name E. You know, kind of like pi has its own symbol, right? Pi 3.14159, blah blah blah. Yeah, a very famous irrational number. Well, A, some people think is just as famous. Okay, so E. This is the definition here, and I gave you the with the limit definition. So this is just saying as your n, this just means as n gets increasingly large, okay? So like let's imagine if n was 2 for a minute, okay? 1 plus 1 half, 3 halves, 3 halves squared, okay, so they 9/4, right? Whatever that is. So as this gets bigger, so now we're going to let it be bigger now. Okay, and then we'll let it be bigger. We'll let it be 4 and 4. Anyways, as this number gets bigger and bigger and bigger and bigger, it approaches, I'm going to do this real fast, it approaches uh, the actual exact value, okay, so, which is 2.718228, blah, 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 okay, so if you can remember, keep in your mind that E is a number, very famous E, an irrational number, so in decimal form, it will never terminate nor repeat a pattern. And just remember that it's 2.718. If you can remember it up to that point, just like you know that pi is 3.14, you should know that E is 2.718. Okay, so remember that. And then you're just going to run, in this section, we're just going to run through some examples with that base E. Okay, so for example, we'll simplify some with some natural bases. You know, E squared times E to the 6. Well, just apply the formula, E to the 2 plus 6, so E to the 8th, which is some number. That's just like 2.718 to the 8th, right? How about 6e to the 4th over 2e to the 3rd? So you go 6 over 2 is 3. You got 4 e's on top, right? So you're just left with 1 on top, aren't you? So 3e. And of course you could have gone 4 minus 3, the exponents, which is e to the 1, right? If you want to do it that way. Think about it that way. Okay. How about this one? Negative 4. Whoops. Extend this a little bit. Alright, so this is using the power of a product property. So we got to take that negative 4 and square it, and then we take that e to the 3x, and then we square. So negative 4 squared, of course, is 16. E to the 3x, that's the power of a power here. You're just going to multiply that, e to the 6x. So 16 e to the 6x. Okay? Um, make sure that you can punch in some with your calculator, your scientific calculator. So just punch this in. Let's go. How about e to the negative 3? Okay, if you have a TI-89, you just find the E button. So you go line button, and it's right above the X button. Okay, E to the, punch in negative 3, enter, and you get 0.049787. 0.049787. You just cut that off to 2 or 3 decimals, of course. Why don't you punch in e to the 0.7, e to the 0.7, and you should get 2.013, 2.014. If I round that to the 3rd decimal there. Okay, so you can evaluate some with that base value of e. Just remember again, e is just a number, 2.718. Okay, you can do some expressions, simplification in your homework like that. Now, what if we were to actually graph e? Okay, what would this behave like? So let's graph, if we let f of x be e to the x, what would that look like? Well, which form does it fit? Does it fit the old exponential growth or exponential decay? And if you remember exponential growth, a was positive, b was bigger than 1. Exponential decay, that a was positive, b was between 0 and 1, okay? So you're looking at that e and you're like, hey, that e is my b, right? And I have a 1 in front for my a. What is e? 2.718. which is bigger than 1. So this thing is an exponential growth. It's going to look like an exponential growth model here. Okay? And like you would expect, we'll just plug some values in. So let's plug in 0, e to the 0, anything to the 0 is 1. Let's plug in 1. Plug in 1. E to the 1. Well, that's approximately 2.718, right? 2.718. Or E. Plug in 2. E squared, which is some, I don't know, 2.718 squared, right? 3, E cubed, whatever that is. Let's go to the left. How about negative 1? E to the negative 1. 1 over E, which is 1 over 2.718, right? Oops, 2.718. Okay, negative 2, that's e to the negative 2. 1 over e squared, whatever that is, okay? And we use our calculator to kind of assist us here with those decimals to see what this function, how this e to the x behaves. Okay, 0, 1, so it goes through that nice classic point there. 1, comma, e, or 1, comma, 2.718. 2, comma, I better punch that in. Okay, so e squared ends up being 7.389. So about 7.4, so 2 comma 7.4, kind of shoots up pretty fast, doesn't that, right there? Negative 1 and would be 1 over 2.71a, so, you know, a little above 1 half here. Or, I'm sorry, a little below 1 half. Okay, I got negative 2.135. Just 0.135 and so on. But anyways, it's getting smaller, smaller, smaller this way. So I again have this horizontal asymptote, y equals 0, domain all real numbers, range y greater than 0. And of course you could shift that around, bump it up, down, left, right, just like we talked about in our exponential growth video. So we'll work on that with our when we get to class as well. Now there's one more, there's an application here to um, compound interest. If you remember our compound interest formula, was the account balance was the principal amount times 1 plus the interest rate over n compoundings to the n compoundings times t in years, right? Now if you let those compoundings keep getting larger and larger and larger, right? So you go from annual, so 1, and then you say, well, let me let it be quarterly 4. No, let me let it be bigger. Let me let the n now be 12 monthly. No, let me let it be daily 365. Anyways, as you let this n get larger and larger and larger, okay, what happens is as you have continuous compounding, so you're compounding every moment of every day, this becomes your formula. So as that n rolls to infinity, your account balance equals PE to the RT. So that's anytime you hear if something is compounding continuously. Now, I've never heard of a bank use continuous compounding, but this is the formula that they would use, okay? So for example, let's say we deposit 1,400 bucks in an account that pays 4% um, annual interest, compounded continuously though. Compounded continuously. That's continuously shortened. What's the balance after 1 year? After 1 year. Say, oh, compounded continuously. There's my formula. Now it's the principal times E to the R times RT. Okay? So this becomes our principal. How much do we put in at the beginning? E, our interest rate's 4%, so 0.04. And how many years? 1 year. Okay. So then I plug in E to the, and of course you got 0.04 times 1, so just 0.04 up there is our power. E to the 0.04 is 1.041. And then multiply it by that 1400 in front. You get 1457.14. And that is how much money you'd have after 1 year if it compounded continuously. Okay, see you guys soon.